Hey guys, Noah here, and today I'm going to be doing Chemistry Honors Unit 3, Atomic Theory, Structure, and Radioactivity. So let's get right into it. So we start off in 460 BC with Democritus, and he proves that all matter, including space and time, was made of small units named atoms. He had no experiments or evidence to back this up, but future scientists did go along with this idea. And then we fast forward to 1803 with Dalton. And Dalton agreed with this premise, but he also stated that compounds are created by combining two atoms, and that atoms of the same element are identical in their mass and properties. Mendeleev, and then we have Mendeleev in 1869, and he created the periodic table, which organized elements according to their similarities. And his periodic law stated that physical and chemical properties of elements are periodic functions of their atomic numbers. And then we have Goldstein in 1885, which discovered positively charged particles. And then we have Henry Becquerel, which discovered radioactivity, and he earned a Nobel Prize for that. And he also discovered that rays emitted from uranium cause gases to ionize. And then we have J.J. Thomson. He discovered the electron, and he experimented by testing and studying the nature of electric discharge in a high vacuum cathode ray tube. And then we have Ernest Rutherford, and his most famous experiment was the gold foil experiment, which he shot a beam of alpha particles at a piece of gold foil, and some of the most of the alpha particles passed through the gold foil, but a few were scattered backward, and this proved that the atom is mostly full of empty space surrounding a nucleus. And then we have Millikan, which he used an oil drop experiment to determine the charge of a single electron. And then we have Niels Bohr in 1913, and he explained that outer orbits in an atom could hold more electrons than inner orbits, and by knowing this, one could determine the chemical properties of an atom. And he also gave birth to the idea that electrons emit light by jumping orbits. And then we have Frederick Soddy as well in the same year, and he came up with the concept of isotopes, and he explained with Ernest Rutherford that radiation is due to the transmutation of elements. Heisenberg, and he thought of the uncertainty principle, and this principle states that one can never know the exact location and energy of an electron simultaneously. And then finally in 1932 we have Chadwick, which discovered the neutron, and the neutron helps balance out protons in the nucleus of the atom. And we have the progression of the atomic model over time. So we start off with a plum pudding model, and scientists, and then the Rutherford model, and then scientists realized that positively charged alpha particles were being repelled and deflected by a tiny concentration. This was in the Rutherford experiment, where some of the particles did not pass through the gold foil, in the center of the atom, and they determined that the nucleus was where that empty space stopped. And as a result of this experiment, the plum pudding model was replaced by the nuclear model of the atom, as it showed generally empty space and then a nucleus in the center. And then we have the shell model versus the quantum mechanic model. And so before the quantum mechanic model, we had the shell model. And we have discovered more characteristics of electrons over time that help develop the quantum mechanic model. And both are great at making predictions. But the shell model is based off Coulomb's law, interactions between protons and electrons. And we learned that you can never know the exact location of electron. So they technically are in a cloud of probability. And so an orbital was a term created to place electrons, and you can only have two electrons in the original shell model and and the problem with the shell model is the uncertainty of where electrons will be, and they're not necessarily going to be in that shell. So the quantum mechanical model was created in 1926 and placed electrons in clouds around the nucleus instead of in a determined place. And so we have atomic structure and changes. So in the center and the nucleus of an atom, we'll have protons and neutrons. And so a neutron is going to have a charge of 0, and it's going to be located in the nucleus, and its relative mass is going to be 1. And then a proton is going to have a charge of +1. It's also going to be located in the nucleus. And then the electrons are going to be located in clouds around the nucleus, and to have a -1 charge, and its relative mass is 1 over 1,840. And now we have what is an isotope. So an isotope are atoms of the same element that have the same number of protons, but a different number of neutrons, meaning their mass number varies. So, for example, hydrogen, it has 3 naturally occurring isotopes. So we can look at example here, and we see that the top A is going to be the mass number, so protons plus neutrons, and the atomic number is going to be Z, so the number of protons, and then whatever the element is going to be E. And so if we look here, we could see that a normal, or like a 1H is going isotope is going to have the same number of protons, and then it's going to have extra, like 2H is going to, sorry. Then the mass number is going to increase, but the atomic number is going to stay the same because the amount of neutrons is changing. Sorry, that took a while to say. And then for you again. Okay. This is another example showing how this works. And then we have cations versus anions. So cations, you can remember, is sort of like a cat. It's pretty happy. It's going to be positively charged. And there's going to be more protons than there are electrons. And then an anion is going to be negatively charged. It's sort of like an onion. You're crying. Miss Clark helped me learn that. And there's going to be more electrons than protons. And then here's just a couple examples. So cation, you're going to be losing electrons or less electrons, so it'll be a positive charge, and then anion is going to have a negative charge. And then they're going to form compounds. Now we have the four fundamental forces. Gravity. So gravity is the attraction between two objects that have the same mass or energy, whether this is seen from dropping a rock from a bridge, a planet orbiting a star, or the moon causing ocean tides. It's probably the most intuitive to remember and familiar. We all grow up knowing what gravity is. It's also one of the most challenging for scientists to explain, though. And we can have a notable figure. Isaac Newton was the first to propose it. Electromagnetic force, also known as Lorentz force, acts between charged particles. So that negatively charged electrons and positively charged protons, and opposite charges attract one another, while like charges repel. And the greater the charge, the greater the force, and much like gravity, the force can be felt from an infinite distance. And then as the distance increases, the force will be felt at a very small rate. And then we have strong nuclear force. So it's the strongest of the four fundamental forces of nature, and it's 6,000 trillion. So kind of hard to say, tongue twister. Times stronger than the force of gravity. That's just because it binds the fundamental particles of matter together to form larger particles, and it holds together the quarks that make up protons and neutrons, and the parts of the strong force also keep the protons and neutrons of the atom's nucleus together. And it only operates when subatomic particles are extremely close to one another. And we have the weak force, and the weak force, also called weak nuclear interaction, is responsible for particle decay, and this is the little change of one type of subatomic particle into another. So that's right. Okay, so a neutrino, I don't even know. That's very close to a neutron can turn a neutron into a proton while it becomes an electron. And then ordered from strongest to weakest, we have the strongest nuclear. So the strongest nuclear force is going to be the strongest, then electromagnetic force, then weak nuclear force, and then gravity is going to be the weakest. Now we have the hydrogen Bohr model. And so Bohr's model can be seen as semi-classical. So it's based on three ideas. So the first is that an electron moves around the nucleus in a circular orbit. The second is that an electron's angular momentum, in the orbit is quantized. And three, the change in an electron's energy as it makes a quantum jump from one orbital to another is always accompanied by the emission or absorption of a photon. And so it's taking on old ideas and also building on them because it adds the idea, or it takes the idea that there's an electron orbit, and then it takes like new ideas like quantization and photons and stuff like that. And we have the Bohr model of hydrogen in terms of the emission spectrum. So Bohr tells us that the electrons in the hydrogen atom can only occupy discrete orbits around the nucleus, not at any distance from it, but a certain like quantized position where they not radiate energy. And when the electron moves from one allowed orbit to another, it emits or absorbs photons of energy, matching exactly the separation between the energies. So then we have valence electrons. Valence electrons are the electrons in the outermost shell of an energy level of an atom. So any element in group 1 has just one valence electron. So examples include hydrogen, lithium, and sodium. And any element in group 18 has 8 valence electrons, except for helium, which has a total of just 2 electrons. So we have neon, argon, all of those. And we have electron configuration. So to calculate an electron configuration, we must divide the periodic table into its sections. So we have the S block, the D block, the P block, the F block. And so the elements in 1 and 2 are going to be the S block, 3 through 12 are the D block, and 13 through 18 are the P block. And then the rows on the bottom are going to be the F block. And then so we have the energy level is going to be the first number, so 1s, so the energy level, or 2s or 3d, that's going to be the energy level. And the number of electrons in that orbital, or in that, like that atom has, are going to be in this top number, and then the type of orbital is going to be here. So that's how you're going to write electron configuration. And so let's take an example. So boron, it's going to be 1s2, 2s2, 2p1, and we're going to see that here, 1s2, 1s2, 2s2, 2p1. Same thing all the way down here to oxygen. And then, so you can write elements in noble gas configuration as well. So for example, bromine, the electron configuration is going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. And instead of writing out all of that, you can start from the nearest noble gas, which is going to be above it. So argon, and you're going to put it in brackets. And then you can start from the energy level after that one. So it's going to be 4s2, 3d10, 4p5. So you're writing a lot less, but you can do it from that noble gas. So determining the number of valence electrons from electron configuration. So valence electrons can be found by determining the electronic configurations of elements, and then after doing that, the number of electrons in the outermost shell is going to give the total number of valence electrons of that element. So we can take bromine. So it has 4s2, 3d10, 4p5 from its noble gas, which is argon above it. And in the outermost shell, our outermost shell is going to be 4s2 and 4p5. So we can add the electrons from that, and it's going to have 7 valence electrons, because those two are going to be the outermost energy level. We don't take the 3D because it's a lower level. Yeah. So predicting the number of electrons lost or gained in the oxidation number based off electron configuration. So we can do this by looking at the element, right? So let's take for example lead. And so we're going to start at xenon, and it's going to go 6s2, 4f14, 5d10, 6p2. And so we can see from that so S is going to be before P and before D and before F. So there's going to be two options for oxidation numbers here. And we can see that it's either going to be a +2 where it only takes from the P, or it's going to be a +4 where it takes 2 from the S and 2 from the P. And so you could do that from another element as well. That'd be the same thing. You just do it from the outermost energy level. And so now we have chemical versus nuclear reactions. And so nuclear reactions involve a change in an atom's nucleus, and it usually is going to produce a different element. And chemical reactions, on the other hand, involve a rearrangement of electrons and do not involve a change in nuclei. And in a nuclear reaction, the mass is not strictly conserved, and some of the mass could be converted into energy. And we can see another comparison. So atoms are rearranged in chemical reactions by the breaking and forming of chemical bonds. Only electrons in atomic or molecular orbitals are involved in the breaking and forming of bonds. Reactions are accompanied by absorption or release of relatively small amounts of energy, and rates of reaction are influenced by temperature, pressure, concentration, and catalysts. And then for nuclear reactions, elements or isotopes of the same elements are converted from one to another. Protons, neutrons, electrons, and other elementary particles may be involved. Reactions are accompanied by absorption or release of tremendous amounts of energy, and rates of reaction normally are not affected by temperature, pressure, or catalysts. And so now we have radioactive decay. So radioactive decay is going to be the loss of elementary particles from unstable nucleus, ultimately changing the unstable element into another more stable element. And there are going to be 5 types of radioactive decay: alpha emission, beta emission, positron emission, electron capture, and gamma emission. Okay, so your mass number is going to decrease by 4, and then the atomic number is going to decrease by 2. And then the for a beta decay, it's going to be the beta symbol, and it's going to have your mass numbers be unchanged, and your atomic number is going to increase by 1. Gamma decay, both are going to be unchanged. And then the positron emission is going to be your mass number is unchanged, and your atomic number is decreased by 1. And then for electron capture, it's going to be your mass number is unchanged, and your mass number is going to be unchanged, and your atomic number is going to be decreased by 1 as well. And then we have fission versus fusion. So fission is going to be the splitting of a heavy nucleus into a lighter nuclei, and fusion is the combining of a nuclei to form a bigger and heavier nucleus. So the consequences of both is absorption or release of energy, and a chain reaction is a series of reactions that are triggered by the initial reaction. And then again, fusion is going to be combining lighter atomic nuclei to form a heavier nucleus, and energy is absorbed or released by the process of the resulting nuclei. Energy is absorbed or released by the process, and the resulting nuclei is lighter than the combined masses of the two original nuclei added together. And this type of fusion may be termed nuclear fusion. That's what we're talking about. And we have safety issues with nuclear reactions. Radioactive decay, radiation can either kill cells, damage DNA within them, which damages their ability to reproduce and can eventually lead to cancer. And when radiation is present, high energy particles pass through your body, and they can collide with atoms in your body and disrupt atomic structure. Then we have fission, and its concerns about the safety of nuclear fission include the possibility of radiation, and this is in terms of it actually being used. So it's going to have a possibility of radiation, releasing nuclear accidents, the problem of radioactive waste, and the possibility of contributing to nuclear weapon proliferation. So basically, as it's used, like adding to the idea that more nuclear weapons can be created. And then fusion is going to have similar consequences. So neutron radiation damage and radioactive waste. And then in terms of its use, there could be tritium releases, the burden on coolant resources. So if it's being used in like a reactor or something, outsized operation costs, and increased risk of nuclear weapons proliferation again. All right, thank you guys so much for watching. Yeah.